Hi there, guys. Well, we have just done exercise 3K. We're working towards 3L now, and this is where we deal with the fundamental theorem of algebra, which sounds pretty grand, to be honest. You think it's going to be pretty mind-blowing, this thing, and you end up getting a little statement which seems kind of obvious. Okay, so let's just unpick this a little bit. Okay, so it says the fundamental theorem of algebra is one of the most important theorems in mathematics. It is an algebraic version of the fundamental theorem of arithmetic, which states that every number is either prime or is the product of a unique combination of prime factors. Okay, so I don't know if you know or if you've heard of this before, the fundamental theorem of arithmetic, but it's basically, I'm sure you've used it. It's like saying, well, 20 is the same as 2 times 2 times 5. And there's only one combination of prime numbers, prime factors, which comprise, go together to give you 20 as their product. And I know everyone's kind of done this before. They've said, let's take 100, let's split it up into 2 and 50. Whenever you get a prime, you circle it. And we're getting 2 primes there, 5 and 5. When we get down to primes, we're finished, and then you've got 2 times 2 times 5 times 5. That's your prime factor decomposition. That's essentially the fundamental theorem of arithmetic. Okay, so what's the fundamental theorem of algebra? Well, this is telling us that there exists zeros, and that's pretty much all it tells us. It says, if you've got a polynomial here of degree n, and you can have real or complex coefficients now. So we're not just talking about real coefficients. So all of these a's can be either real or complex. It's saying that there's at least one zero. It's basically saying there must be a solution to this. There must be something in this where we get some value of x where we get a zero. And you can think of that kind of practically by thinking, well, these are continuous functions. So at some stage, they're going to cross the x-axis. You're going to get a y is equal to 0 round. But then you think, well, oh, hang on a second, what about x squared? That didn't seem to give us 0 sometimes. But that's why we're now saying there's not only real solutions, but there's also possibly complex solutions here as well. And we've talked about this before by saying, well, when we use the quadratic formula, we get a plus or minus the square root of something. Now, sometimes you'll end up getting plus or minus this complex number here, some amount of I, and that will give you 2 complex roots as well. But, the sort of essence of this is to say, well, and sort of just to get you thinking about what this is meaning, is saying, essentially, there is a number that will make this equal to 0. There's a number for what they're calling W here, if you like, which will make this equal to 0. Now, when we say W there, you can see from this Greek alphabet that, in fact, W is actually our Greek letter omega. So you can see down at the bottom here, we've got a capital omega, which you're probably familiar with, and then the lowercase omega, which is kind of less commonly used, is what they're talking about here. So they're letting omega equal to our complex number, but forgive me if I say W every now and then. Okay, so let's just look at this again. So that's this thing here seems a bit of a letdown, given that this is the fundamental theorem of algebra. You kind of would have expected a bit more. Well, in fact, it does lead to a little bit more here. And in fact, it leads to this lemma, which is essentially just a little extension. And let's just take this one. And this is the kind of this is the one version which more people mention in a way, because this is essentially saying that, in fact, there's not only one solution, but so long as there's still a polynomial left, we can keep taking out the next solution. So we can essentially factorize this thing. So once we've taken out one solution for our polynomial with degree xn, so with degree n, then we're left with another polynomial, not necessarily this one here, but whatever we get when we take that factor out, and it's now got a degree 1 less, and now the same thing holds true. There will still be another root which we can take out, or another factor which we can take out, and we can keep doing that until we've run out of powers. So we can keep doing that n times. And you can see that here when we write this as our combination of our factors. We're obviously going to need to stop when we get our highest power of x to the power of n. So we can do this n times. So this is a little bit more important now, because it says that every polynomial we get, when we equal it to 0, we'll end up getting n roots. Now, those n roots can either be real numbers or they can be complex numbers. So that's why, again, they're saying that this omega belongs to your set of complex numbers. And complex numbers can be real as well. They contain the set of real numbers. So we're getting either complex numbers or real numbers. Okay, now this is what I mentioned before, and if we just check this one out here, this is on website Maths is Fun. It says the fundamental theorem of algebra is essentially any polynomial of degree n has n roots. Well, in fact, that's what most people remember, but as you can see from the way the book sets it out as well, it's saying, well, actually, the fundamental theorem of algebra is simply telling us that there is at least one zero, or at least one root. But the extension to that is that you can keep taking out these roots until we've got no polynomial left. So in fact, there are n roots for a polynomial of degree n. Okay, so let's have a look at one of these questions. Now, there is another little extension later on when we deal with complex roots, but we'll deal with that when we get to it. So example 27 says, express this polynomial as a product of linear factors and check your answer by using your calculator. Okay, well, this time it doesn't tell us to divide by any particular linear factor to start off with. So we're kind of stuck at the start here. Where do we go from here? Because normally the question will say, well, we know that one of the factors is maybe, I don't know, for example, x minus 2. So, you know, you can use your Horner's algorithm and you can find out the quotient that you get when you divide by that. And then, of course, you get a remainder of 0 if it's actually a factor. But in this case, we're not being told what one of our factors is. So we're either going to need to be clever about finding an initial factor, or we're going to need to make some guesses. Now, you might be able to see to start off with here that, in fact, you could just factorize out x. So that's going to make life a lot easier. So we've got x cubed minus 6x squared minus 19x and plus 24 there. That's going to be equal to your f of x. So we definitely know that one of our factors is x. And so one of our roots is just simply putting in x is equal to 0. That's pretty obvious. You put in 0 here, you're going to get out a 0 here as well. So that's one of our roots, and that's also x is one of our factors. X, of course, can also be written as x minus 0. Okay, so then how do we find the next factor here? Well, previously, in previous videos, I've said, well, if you're going to factorize this, you've got to realize that those next three factors, let's just call them x minus a, x minus b, x minus c, when you times together this a, b, and c, that's going to be negative in this case as well, that's going to give you 24. Okay, so it means to say that a, b, and c could be any combination of factors of 24, which multiply together to give you 24. For example, it could be, I don't know, get minus 1, and I know, let's go minus 2 and 12. Now we're hoping that these are all real solutions as well, not complex ones. Okay, so in fact, it's quite difficult to know where to go from here. Perhaps you could try plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. But again, you can see that you've got an awful lot of factors here. And, you know, there's so many factors of which we could try out: plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. So that's 16 different numbers which we're trying in for f of x in order to check to see if we've got a factor using the factor theorem. Okay, well, actually, there's a bit of a trick to this one. And I think if you're getting this in an exam situation, you've just got to take a moment to think, really, am I going to try and go through each of these things? Now, it's possible on your calculator, if you don't see the trick to this one, it's possible on your calculator to define f of x. And we looked at that in a previous video. That's fairly straightforward to do. So define f of x as this function here. And then you can just do f1 and f minus 1 and so on. And actually, you can do those calculations really quickly if you've defined this function on your calculator with GDC. But if this is not using your calculator, if this is on a non-calculator paper, then you really need to just stop for a moment. Now, okay, now here's the little trick. And you might notice that the coefficients that we've got here are 1, minus 6, minus 19, and plus 24. Now, when you add all of those things together, we can see here we're getting minus 25, plus the 1 gives us minus 24, and add the 24 gives us 0. So the coefficients are straight away giving us the answer of 0 if we add those together. So that essentially means that we just need to put in x is equal to plus 1 in here, because then all of your powers of x will essentially disappear. They'll become 1, and you'll just end up with this sum here. Now, obviously, if you went through this list, you'd start with the easiest number, so you'd start with plus 1 anyway. So, yeah, this is not necessarily easy, this question, or easy to see how you're going to start. But there is a little bit of guesswork there going on. Okay, so let's just see if I can take back this. No, I can't. Okay, so let's now use Horner's algorithm to take us a little bit further. So we want to use Horner's algorithm on this. We're saying that's going to be 1 minus 6 minus 19 and plus 24 there. And our factor that we're dividing by here is x minus 1, because we realized that f of 1 gives us a 0. So we want to substitute 1 in. Of course, that's Horner's algorithm again. And we're taking the 1 down. Remember, we're putting our pluses in front of these. So we'll take the 1 down here, and 1 times 1 is 1. And then we're getting minus 5 there. We add these two things together. Then minus 5 times by 1 gives us minus 5, which is then giving us minus 24 there. And times by 1 again gives us minus 24. That gives us 0. So we've got a remainder of 0, which is telling us that that is a factor, which is what we want. Now, the whole reason of us doing this is to get the quotient out. The quotient, as explained in previous videos, is this part here. These are the coefficients of your x squared x and your constant term. So we're now getting f of x is equal to x minus 1, and our quotient, I'm missing my original x there, x and x minus 1, there was the original x. And then we're getting the quotient as x squared minus 5x and minus 24. Okay, so there's f of x. We've now brought it down to this stage here. Now, with this last one, you can just factorize a quadratic if it does factorize, or you could use the quadratic formula to see what your roots are. And then, you know, if you get your root is, I don't know, for example, x1 is one of your roots, then you can set up your bracket saying x1. Of course, that might be complex, that might be a fraction. We're not sure. But with this part here, this is pretty straightforward to factorize. We can see that we need two numbers which times together to give minus 24 and add together to give minus 5. That's going to be x minus 8 and x plus 3. So there's our final two factors, and there's our final answer in this case. Okay, let's just have a little look at how the book does that one. It's done it in a very similar way. Now, it's done a few extra lines talking about how to factorize a quadratic there. I'm sure you all know how to factorize a quadratic by now. There is a good little extra bit here on the end where it talks about finding polynomial roots using your calculator. Whatever calculator you have, and obviously we have the TI Inspire at our school, and that's what I recommend you to get. So there is this technique using the TI Inspire, the CX model. It says if you want to find the roots of your polynomial, you can type in your polynomial. You don't need to put in an equals to 0 there. Okay, you'll notice they haven't done that. So it's just the polynomial taken to one side equal to 0, but you only need to put in the f of x. So put in the f of x, comma x, that's defining the variable which we're working in. And you need to just say polyroots for that one, and it will give you all of your solutions. Now, you can do that in terms of the real roots, or you can do it in terms of complex roots when you go through the menu. It will ask you whether or not you want real roots or complex roots. If you always go complex roots, even if all your roots are real, that will still be fine. It will give you all of those because, again, to remind you, real numbers are a subset of complex numbers. But if you only want the real solutions, then of course you'll go to real solutions when you go through the menu to find your roots here. Now, of course, that's your set of answers. That means to say there's 4 answers there. And of course, you're expecting 4 answers if you're going to go for complex roots. There will always be 4 answers for a quartic, where your highest power is to this polynomial is x to the power 4. Okay, next question then. Okay, so there's a little extra in the middle here. It's saying, defining what multiplicity is. And it says, if a certain factor appears more than once, we say the factor has multiplicity. So, for example, if you have, I don't know, f of x is equal to this quadratic here, what we normally say is that we have a repeated root here. And if you draw your graph, that would be saying, well, we have a repeated root at 1. It would look something like this. Okay, so a translation of 1 in the positive x direction from the x squared graph, taking us to this graph here, something like this. Also crossing through 1 as well. Okay, now we'd normally say that there's a repeated root in this situation here. And the way they're saying it now is that that root has multiplicity, or rather the factor has multiplicity. And likewise, in the question, when we have a look at example 28, they're saying -1 is a 0 of this polynomial with multiplicity 3. So they haven't said the factor has multiplicity 3 there. They've said the 0 has a multiplicity 3. Now, what's interesting about that is if we go back to the lemma of the fundamental theorem of algebra, which tells us that we're expecting n solutions to this f of x is equal to 0, that we're expecting n roots to a polynomial equation with degree n. It doesn't say that those roots have to be distinct and different, essentially. So some of them can be repeated, but we'll learn in a little bit as well that, in fact, there's a relationship between the complex factors. Okay, but these roots don't have to be different. They could be, if you want, this x minus omega, and you can call it omega 1 if you want, to the power of n. That would be fine as well. So you'd have n roots which are all the same, but it still has n roots. It's just some of them are repeated. Okay, so let's have a look at the next question. We've got example 27. Okay, and we're still dealing with, sorry, not example 27, we've done that one already, haven't we? Next one, sorry, example 28. Now, I think we're still dealing with only real roots in this case as well. And so this one is saying -1 is a 0 of this polynomial with multiplicity 3. And it says express f of x as the product of linear factors. Okay, well, check it out. This one is huge. We've got to think about dividing this many times in order to get down to a quadratic that we would know quite easily how to factorize. Now, fortunately, we know that we can divide it 3 times by the factor x plus 1. Okay, so we can divide by x plus 1 to the power of 3. We can do that because we know that x plus 1 exists in this function 3 times over. Okay, and when you put -1 in, you get 0 3 times over from 3 different brackets, essentially. And then you're left with your quotient over here. There won't be a remainder because we're talking about factors here, and factors don't leave remainders. And so this is going to be your f of x, and your quotient of x here is going to be an x squared function. So this is going to be some function of x, but this is going to be a quadratic at the end, and then we can just factorize that last one, hopefully fairly easily. Okay, of course. Okay, so let's deal with our algorithm again. So we've got 2, 7, 3, -13, -17, and -6. This is our synthetic division that we're doing yet again, and we're going to put a times by 1 on the side. No, we're not going to put a times by -1 on the side because, of course, when you substitute -1 in here, that's the thing that gives you your 0. And we're going to bring down that 2, and we're going to put that plus in front of each of these things here. Now, obviously, I'm going to do this 3 times here. So if you find this a little bit tedious, or if you want to have a go at this yourself, then just stop the video up, practice having a go at this yourself, get a bit more practice with Horner's algorithm or the synthetic division, and you can just check through with my answers as I go through. Okay, now times by -1, and so we're getting here -2. 7 plus -2 is 5. 5 times -1 is going to go here. We're going to get the -2 here. -1 times by -2 gives us 2. Going to give us a total of -11. Times by -1 is 11. And then we can get -6 when we add those two terms together. And then -1 times by that gives us +6, and just what we were expecting. The check for us, given that we know that this is a factor, is 0. So there we go. That's the first time around when we take out this factor of x plus 1. And the quotient which is left is, in fact, 2x to the 4 plus 5x cubed, and so on. Now, we want to get down to the stage where we've got a quadratic, so we're going to do this again. And we're going to take that quotient and split it up again. So we're going to factorize out another one of these x plus 1s. Let's take the 2 down. Let's remember to put all of our pluses underneath. And we're hoping to get out a 0 at the end in this position this time. So let's do it again. So we've got -2 times by, 2 times by -1 gives us -2. So that's +3 there. Times by -1. And then add them together, we get -5. Times by -1, add them together, we get -6. Times by -1 is +6 again. And there we go, we're getting our answer of 0. So we're getting our 0, which confirms that it was again a factor. And we need to do that one more time. And again, we're going to take the 2 down, times by -1. And we're going to put a plus here. Sorry for the question getting in the way. So times by -1, we're going to get -2. 3 plus -2 gives us 1. Times by -1 gives us -1, which gives us -6 again. Times by -1 gives us +6, and then we get our 0 here as well. Okay, so now we can see that our f of x is equal to x plus 1 cubed. And then we're left with this as our quotient. So we're getting 2x squared plus x minus 6 is our quotient. I'm hoping that this one factorizes. So let's think about whether that does. Now, obviously, one of them is going to be 2x. One of them is going to be x. And I suspect that we're going to have a 2 and a 3 inside. And probably it's not a 2 here. I'm expecting that it might be a 2 there and a 3 there. Let's just see. Yeah, it seems so, right? So when we do 2 times 2x, we're getting 4x. And so that can be plus. And then we're going to get a minus here in the middle to give us minus 3x there. So we're getting the middle terms of 4x minus 3x gives us plus x there. Now, obviously, you've got a technique for doing that, but you can make your guesses like I've done there. If you think there's not many factors to go through and not many possible combinations to go through, you can just do it by a bit of trial and error. Okay, well, there we go. We've completed that one. That's now fully factorized. And obviously the question says check your answers by using your calculator, or you can do your poly roots for this one as well. Let's just see what the book does. And there we go. They've got the same answer as us. There we go. And there we go. When you'll notice that when you check with poly roots on your calculator, it will give you that full set. And although -1 is the same as -1 in that set of numbers, they're actually going to give you all 5 solutions, so that you can see which factor has been repeated. So we've got that -1 3 times over there. Okay, so which is telling us that x plus 1 is your factor. Okay, but -1 is giving you your 0. Okay. A little investigation going on here. And I'm going to skip past that just for a moment because I'll just explain this one anyway. This one says the conjugate root theorem. Okay, so this is pretty interesting. Now we're getting on to complex solutions. Now remember, just take a little bit here. Okay, now remember that when we're dealing with a quadratic, for example, our solutions are minus b plus minus the square root of this b squared minus 4ac divided by 2a. Now, every time that we get quadratics, complex solutions, it always comes from having to do at some stage the square root of a negative number. Now, that's being solved in an equation situation. Now, seeing as we're solving we're essentially undoing a square. And so at some stage, we're having to do the square root of a negative number. Now, because that's in an equation situation, you always get plus or minus there. So that means to say that these complex solutions always come in pairs. Now, you could think, well, what happens when this is 0? Because then you're not going to have a plus or minus something. But then if this is equal to 0, you're not going to have a complex solution. It's going to be real because plus or minus 0 doesn't give you any complex part. So that's not a formal proof, but that's kind of a reason as to why complex solutions, complex roots, always come in pairs. They come as plus the something I. So for example, in this case, we'd end up getting, for x, we'd end up getting plus or minus 5i. So you get the plus imaginary part and you get the negative imaginary part. But the real part, say for example, there was a 2 in front there, the real part always stays the same. So not only do these things come in pairs, they're the complex conjugate of each other. Okay, so in this case, you get 2 plus 5i, and you get 2 minus 5i. Okay, now that's, again, not a proof. That's just an informal explanation of how this is coming about. And they don't provide you with a proof of this one as well. There's an investigation to help you understand and verify that this is the case. So, for example, you can put in, for example, for 1e there, -1 plus 3i, and then try putting in -1 minus 3i. And if they're roots, then you'll notice that they're both obviously the complex conjugate of each other as well. Okay, so there's no proof of that one. In fact, there was no proof of the fundamental theorem of algebra, which was in fact, as mentioned in the book, was proved by Gauss as well. So there's just something that we've used. We can kind of sort of understand it. We can understand that perhaps must be the case, but there is actually no formal proof given for these theorems in the book. Okay, so let's just read the conjugate root theorem again. It's just simply saying, given this polynomial that has a complex zero, then its conjugate z star is also a zero of the polynomial f. Okay, so let's see where that's going in these questions. And I think we've got 2 more questions left here. We've got example 29 and example 30. Okay, so example 29 says, given that 1 plus 3i is a complex zero of the polynomial here, find all of the other zeros of f. Okay, now there's a couple of ways in which you could do this. You might be thinking about going straight to the synthetic division. You might be thinking, okay, well, I'm just simply going to divide by this. However, through this, what do they call it again? The complex conjugate root theorem. Through the conjugate root theorem, we know that this is not only one of our roots, this provides us with the other root as well. So 1 minus 3i is going to be our other root. So we can say that this is already comprised of x minus this number here, okay, and x minus 1 minus 3i. They're definitely going to be 2 roots in this case. Now, what have I done there? I've said, okay, well, they're saying that these are a complex zero. So that's saying, like, for example, W1 is equal to 1 plus 3i. And remember, the format of our factorized polynomial is going to be x minus W1, or omega 1, if you like, and then x take away the next one, and so on. So we've simply done x minus this thing here. Okay, so it might be worth now multiplying this out and then seeing what quadratic we get in this case. And then once we've got that quadratic, we can then figure out what our last solution is. And we can perhaps do that simply by thinking about whatever we're getting out as our last term in that quadratic times by the last term in our last bracket should give us minus 30. That's one potential way of doing this thing. Okay, well, let's actually multiply this out then to start off with. So we're getting x squared from this. We're getting minus 1 plus 3i lots of x. We're getting minus 1 minus 3i lots of x. And we're also getting this times this. And since they're both minus, that's going to be plus 1 plus 3i, and 1 minus 3i as well. You'll notice here, of course, that 1 minus 3i is actually your complex conjugate of 1 plus 3i. So we've got that turning up again here, the product of a complex number and its complex conjugate. Okay, well, let's multiply this thing out now. So we've got x squared, and we've got minus 1 here, minus 1x, and then we're getting minus another x here, so getting minus 2x, and then we're getting minus 3i, and we're getting minus 3ix and plus 3ix. So actually they're going to cancel, and then when we multiply this thing out at the end, we're going to get a real number as well. So we're going to get plus 1. Of course, the 2 middle terms disappear there, and then we're going to get 3i times by minus 3i, which is going to bring us back to plus 9. Okay, 3 times minus 3 is minus 9. I times I is minus 1. So I'm just going to write that down as plus 10 here. We've got x squared minus 2x and then plus 10. So we now know that f of x is equal to our x squared minus 2x plus 10. And given that this thing factorizes, okay, given that this is a complex zero and we're looking for all three factors, then our last one should hopefully be x minus 3 to get that minus 30 here. I mean, there shouldn't be a remainder because we're looking for our other zero. Okay, we're not expecting any remainder in this case. Now, how do you know that for sure? Well, either multiply this one out, or you could do a technique of long division as well. So you could do, or your synthetic division if you like, you could do your 1 minus 5, 16, and minus 30, and then you could divide it by, oh, hang on a second. No, we can't use synthetic division there because we were dividing by a quadratic. Synthetic division is not set up for that. So we then need to go back to our division of polynomials. So you can't completely ditch your technique of long division for division of polynomials. So we've got x cubed minus 5x squared plus 16x minus 30, and then let's divide that by x squared minus 2x plus 10. Now I'm not going to do that in this case. You can multiply this out to verify that's true as well, and I think that's probably the easier thing to do in this case. So we could check out that we're getting x cubed minus 2x squared plus 10x when we multiply everything by x, and when we multiply everything by minus 3, we'll end up getting minus 3 times by x squared, giving us minus 3x squared there. We're getting minus 3 times by minus 2x, so that's giving us plus 6x, and then minus 3 times by plus 10 there, giving us minus 30. Add them together, we're getting x cubed minus 5x squared plus 16x and minus 30, which is verifying that this must be our last factor as well. Okay, I notice in the book they do this method. So you can see that they're doing this long division technique to find the remaining factor there as well. Okay, so the remaining factor is x minus 3. Okay, now that's one method for doing this question, and you might not necessarily think about doing that. You might be in an exam situation feeling the pressure to just plow on with some working out. And another method which you can do, which I'm going to go through now as well, but which you can spend some time doing too, is simply to do your synthetic division or Horner's algorithm twice by starting with this first factor, or first zero rather, of 1 plus 3i, or the factor of x minus that value. Okay, so I'm actually going to do that now. If you want to skip ahead, or if you want to try and do this for yourself, then obviously go ahead. So we're going to put down 1 minus 5 and 16 and minus 30 here, and we've got x minus 1 plus 3i is your factor. So we're going to be putting in times by 1 plus 3i here, times by this thing here. Bring the 1 down, put a plus here. Probably going to need some space because we'll end up with expressions in this case. So put pluses in front there. And the first thing we're going to do is times the 1 by this thing here. So we're going to get 1 plus 3i. When we add these things together, we're going to get minus 4 plus 3i. And then when we times that by this thing here, well, that's pretty messy. We're probably going to need to do some working outside for this. So we've got 1 plus 3i times by minus 4 plus 3i. So we're going to get minus 4 there. And let's do the other real numbers. 3i times 3i is going to give you minus 9. So 3 times 3 and then I times I. And then we're going to get minus 12i. That's just the middle terms. And the outer terms here are going to give us plus 3i. So for this one, we're going to get minus 13 and then minus 9i. Okay, so we're going to struggle to fit this one in here. Let me just call that something. Let's call this A, for example. Let's just put that in there. So then when that's there, okay. So when we add that with the 16, we're going to now get 3 minus 9i. Okay, and finally, we're going to need to times this by this. So we've got 1 plus 3i times by 3 minus 9i. We multiply those together, we're going to get 3 and 27 and plus 9i and minus 9i. Okay, so those two things are going to cancel, and we're going to end up getting plus 30 there, and we're happy with that. That checks our working out because minus 30 plus 30 gives us our 0, which means to say that this is a factor. Now we've got the same thing again because this is our quotient. We're going to now divide by the next 0, the next complex 0 is going to be its conjugate. So we're still having to use that factor, in fact. So we're going to say times by 1 minus 3i here. Again, we're going to bring the 1 down, and then we're going to put a plus in front of there, plus in front of there, and hopefully we're going to end up with a 0 here again as well. So we're going to do 1 minus, we don't need to do anything there actually, do we? Because this times by 1. So this is 1 minus 3i. When we add those two things together, we're getting minus 3, adding these two things here. And then the i's are disappearing. So there we go, we're just getting minus 3. And now we need to times, remember, by this thing in front. So we've got 1 minus 3i times by minus 3, minus 3 plus 9i there. And you can see that when we're getting minus 3 plus 9i, it's the negative of this thing up here. When we add those two things together, we're getting a 0. Okay, so a little bit of working out aside, it is fine, by the way, to do your working out aside. And I might even just say, in an exam situation, here's my working out. This is just aside. This is just supporting my main work. It's just some calculations which I've had to do, which are extra. And also, think about how the examiner is approaching the page here. This is looking like a bit of a mess at the moment. So they're thinking, well, do I really need to look at this? No, this is just stuff which is supporting the main working out. So that's why it's good to label that as a side. Okay, now we're left with this final quotient, and this final quotient is just 2 terms. And so that basically gives us the final factor, which is x and then minus 3. So there's another way of getting to the final factor. Here's one factor. That's not the factor, sorry. The factor is going to be x minus this thing here. So we've got 1 plus 3i. That's a factor. This is a factor. And then we've got x minus 3 is our final factor there as well. So there's the final factorization, all done by Horner's algorithm. Okay, right. So this is a bit of a long video, but last one. Yeah, last one before 3L. So we've got example 30. So example 30 says the polynomial is given, and a is a real number. We're missing something here. We're missing one of our coefficients in this case. And it says find the value of a given that 2i is a complex 0 of f. Okay, so if 2i is a complex 0, remember again that that means that x minus 2i is one of our factors, and another one of our factors is going to be x plus 2i. Okay, so I've just had to stop the video there because I ended up with what seemed to be a mistake. But it turns out there's a mistake in the question here. And that will be corrected in newer versions of the textbook. This I'm just using here a PDF, like the original PDF, which was released. Obviously, if you're using the code for the book and the online version, everything has been updated. I'm just using the PDF, obviously, because it's just a little easier to scroll through. Obviously, as a school, we bought a ton of these books. But okay, well, where is the issue here? The issue is the fact that there should be a 2 in front of x to the power 4. Now, I've actually used a different method to the method that the book has used to solve this question. I've said, well, look, seeing as 2i gives us a complex 0, all we need to do is substitute 2i in here, and we'll get 0 out. The book does it a different way. It uses Horner's algorithm, but it comes up with the same process, the same solution, essentially. The problem is that when we start saying this is equal to 0, it's fine to say, look, complex part has got to be equal to the complex part. So that's 0 plus 0i, essentially. And that's fine to say that we're getting out here a is equal to -4, but we can't have -16 is equal to 0. These two expressions are the same, then the real part has to equal to the real part. So at that point, I was scratching my head, and then I thought, okay, well, given that the book seems to think that a is equal to -4, I'll put that in here, and I'll put it in my calculator to find the polynomial roots. And again, it didn't give me 2i as one of my zeros and -2i as one of my zeros as well. So I knew something was up, and I knew there was a problem with my original function. And it turns out that there should be a 2 here. Now, if you think about that, if I put a 2 in there, then this becomes 32, and I've got 16 more, and that disappears. And if you have a look at the book, if you look at the book for this, you can also see that they've got 2 in these blue squares here at part A, doing the synthetic division. They've put 2 minus 1, 2. Well, there was no coefficient of x to the power 4 of 2. It was 1. So that's an issue then. That's an issue with the setup of the original polynomial. Okay, now if we change the question to make a 2 there, then we're getting the 0 that we require, and we're saying this is equal to 0, and it's also equal to 0i as well. So we can simply say at that point 2a plus a is equal to 0, and therefore a is equal to -4, and we are done. So it was an adjustment to the question that was needed. Now you can see that I've got one method here. The book has another method. You could likewise, instead of putting in 2i, you could also have put in -2i. It would have been slightly more complicated. My working out, by the way, in order to do that, I just came up with a little table for I to the 0 and I to the power of, down to I to the power of 5, just to get out my powers of I for making it easier when I was multiplying these things out here as well. Okay. So yeah, you could put in as well f of -2i, and that should also give you 0, and that will also give you the same answer as a is equal to -4, provided that you put this 2 in front. Yes, so there you go. That will also give you the answer too. But of course, it's slightly easier doing f of 2i. Now, to answer part B, where it says, hence find all the remaining zeros, we're going to need to completely factorize this thing. And again, you've got two options as to how to do this. You could either do it like we did the previous one by saying, well, we know that x minus 2i is a factor. We know that x plus 2i is a factor. We can multiply those two things out, and then we can divide our polynomial, now knowing that a is equal to -4. There's a 2 in front of there again, of course. And we can divide our remaining polynomial by this. We'll end up with a quadratic, and then you can factorize that quadratic, or you can find the solutions of that quadratic by using the quadratic formula. Or alternatively, if you did the first part using synthetic division, then you will already have a quotient, which you can now divide by the next factor, essentially. So if we've put in all of our numbers, 2, -1, 2, -4, and -24, if we've done this, or rather we found that we've got -4 out there, and we've got our expressions in terms of a, and we can then just substitute back in the -4, and we've done that for putting in 2i, the next thing to do would be to put this thing in, put in minus 2i, and again we'll bring that 2 down, and then whatever we're getting is our quotient here. Even if it's in terms of a, we can then substitute a in. Then we're going to do the same process again with minus 2i. And then, of course, you're going to end up with a quotient which is a quadratic, and then you can factorize that as normal. Now, from my point of view, I've just done the first part by substituting in 2i, and I found that a is equal to minus 4. So my next step here would be to multiply out these two factors and then do my long division approach by dividing by my two factors there. And then I would then factorize my quotient. The book has done it differently. And so the book then, because they've got the Horner's algorithm, because they've used the synthetic division in the first place, they can now substitute in a. So they can find that we've got our coefficients of the quotient is 2, and then minus 1 plus 4i, the same as above, minus 6 minus 2i, same as above. And then when we substitute in a is equal to minus 4, we'll get 4, minus 4 disappears, and then we get minus 12i as our coefficient of x to the power of 0 in our quotient. Okay, and then they've done the algorithm again with minus 2i. Now, it's your choice how you want to do this. I would probably do this, as I say, by doing this process here. I've not used the algorithm in the first place for part A. Okay, well, I'm going to stop there. I've done an awful lot of talking. There's an awful lot to digest. Thank you for listening. Good luck with the exercises. And we've got 3L. There's now 6 questions in that exercise. And the next bit coming up is all about sums and products of polynomial roots. Okay, guys, well, thanks for listening, and hopefully see you next time.